Hello class, we're going to go over a recorded lecture here from chapter 3 and introduce you to the voltage clamp.
And so what we have here is, we've got our squid axon. Let me change colors here. Good. And we've got a little device. We have a microelectrode that is inserted into the squid axon. And what this does is it detects the voltage. Picks up into this electrode, right, into the flow of electricity. It's this way until we get to our measuring device. This is measuring the membrane potentials. Measuring our membrane potential. So our little dial here tells us what's going on inside the neuron. All right, in this little bit right here is our ground, or telling us what to compare this to, right? And so this is just outside of the neuron. And we have an extra little bit here. Now this sort of goes beyond just being able to detect the membrane potential. We actually have something here that is called our command voltage. Or more appropriately, the command voltage control. It's a little device that allows us to pump charge into our neuron. So it can actually change the membrane potential. Maybe we want it to, so you can think of this command control as just this little, it could be a little box. Typically these days it's it's digitized, so it's a computer. But you can imagine little buttons for different voltages, -70, -30, 0. Or you could also make it positive. We could make it +20. We could go really high, +75. Really, there really isn't too much limit here, right? And all of these values are millivolts. Same measurement as our membrane potential. And so we can press a button and say, okay, a resting membrane potential of the squid axon is typically -65, but we could press it and say, okay, beep, command voltage. After detecting that it's -65, it's going to pump in +65 current to counteract that and make it 0. And it does this in real time. So it's very responsive. So responsive that you really don't detect any sort of fluctuation in the membrane as you're measuring it here. And we have a nice little dial here that is going to tell us exactly how much current our command control has to pump in. And this will give us insight into the dynamics of the axon of what's going on. So let's take a close look at that. Okay, so we have the top row here, color-coded the same as green. This is our voltage clamp command, and actually that's a little misleading here. Anyway, we're not going to call this the voltage clamp command. This is our passive measuring. So this is, the top is this dial here. It's what's measuring our membrane potential. So it's green. This is what it's pumping out. And this is what we can use to change or this is what will reflect once we push a button here and say, okay, make it 0. This is going to show us that this is pretty constantly 0. And then this is going to tell us what's going on with the charge that we have to pump in to make it 0. So this should be relatively static, unless we push a button and change it all of a sudden. And this should be perhaps dynamic, depending on the charge it has to pump in. And so that's our little triangle dial telling us what our membrane potential is, what it's registering. And this down here is our voltage command output. It's what is being pumped in. And so if we ask it, make sure that the resting membrane potential is -65, which is what it is naturally. So there's nothing goofy about this squid axon. We should not have to pump in any kind of charge because it's already at -65. So our voltage clamp output should be 0. And this is what we would observe. Now, let's change it. We're going to tell our command that we want it at -65. This is a hyperpolarization, right? Because we're making it more negative. What do we see? What does the command voltage pump in? Well, when it gets to this period, when we push the button, we see that the command control pumps in a quick burst of negative current. It lowers it, and it's set. The command voltage does not have to continue to pump it in. It pumps it in once, and that is enough to keep it there. A little bit of negative charge hyperpolarizes a neuron. That was pretty straightforward. Nothing too exciting, nothing too dynamic. So let's take the opposite. Let's take a look and see what happens when we depolarize. So we're going from -65 to 0, which requires the command control to pump in +65 millivolts worth of charge, right? And this is a depolarization. So as you might expect, when we push that button, it's like, all right, got to make you 0. Let's pump in some positive charge equal to the resting membrane potential. So you get a nice little spike here in charge that's that's equal to what you need to bring -65 to 0. All of a sudden, you see that it starts to pump in negative charge. It peaks, and then it wanes again and comes back to 0. But it doesn't stop there. Now it reverts back to positive charge a second time. And then it constantly pumps in a positive charge in order to maintain a 0 membrane potential. So this command control is working. It's continually working. First, very dynamically, a quick burst of positive charge, and then it reverts to a fairly quick input of negative charge. Then it goes positive again and plateaus. And now it's constantly pumping out a positive charge to keep this at 0. Right, so something's happening inside the axon that wants to pull it back down to -65. And that's why this is continually having to pump in positive charge to say, nope, you're not going back down to -65. I have instructions to keep you at 0. And so this lets us know that there are 2 types of ion currents going on here. And if you think about the command, it's pumping in the opposite of what the axon is bringing in. Right, so we have to pump in a negative charge because there must be some sort of flood of positive charge coming into the axon from somewhere else that the command control does not have control over. And likewise, when the command control is constantly pumping in this positive charge, that means there must be a source of negative charge coming back into the axon that the command control, that the voltage clamp has no control over. So we see during this dynamic process here, we have this transient inward current. Because it's negative, there must be some positive inward current, positive current coming into the axon. And then we call this an outward current. It's a delayed outward current. So our transient inward and our delayed outward current. And so let me just write that here. Transient inward current in our delayed outward current. So very dynamic when we depolarize our axon. Way different than when we simply just want to hyperpolarize. Easy, piece of cake. But super exciting there. See if we can get a little better idea of what's going on. One way we might want to do that is sort of take a look at what happens when we do various different, setting the membrane potential of various different charges from 0, and we'll go even further and start repolarizing in the positive direction. What do we see? Well, we already know what this looks like, right? We'll transient spike, and then we get this transient inward current, and then we get this delayed outward current. I'm going to make it a little bit more positive now. Get another little spike to get it going, and then we still get a little bit of transient inward current. But eventually we have to pump in a positive current to maintain it at positive 25, right? So there must be some sort of outgoing outward current, positive charges leaking out of the axon somewhere. And we can see that we have to go a little bit higher here. It plateaus higher. We have to put in a little bit extra because we're no longer at 0. We want to go to 25. But this is shallower. And then when we're at positive 55, something interesting happens. We no longer have this outward current. We no longer have this transient inward current. Because if you see here, we don't dip below 0. The command control at no time is having to pump in a negative current. So that must mean that there is no positive current coming into our axon. In a previous lecture, when we took a look at using the Nernst equation to take a look at sodium and what we would expect the membrane potential to be given the concentration of sodium on the inside and the outside and the charge of sodium, we found it to be around positive 55. And so this is what the charge, negative 55. And so the fact that we have positive 55 suggests that the inward current is driven by sodium flooding into our neuron. Because we know that if sodium, given the concentrations, what's on the inside and the outside of the cell, right? So the outside is about 440 micromolars, and on the inside it's significantly less. Off the top of my head, 40 or 20 millimolar. And so we know that if sodium could, it would rush into the cell. And we know because of what drives it, both that electrostatic force it wants to get in, and we also know the concentration it wants to get in. It wants to go from highly concentrated and diffuse to lower concentrated areas. And we know it would eventually settle at 55. And so we see that our positive 55 completely counteracts that. So if we have positive 50.5 inside the axon, that's preventing sodium from getting into the axon because of that electrostatic force that's that equals its membrane equilibrium. And if we go above this, we see that our command control has to pretty much work overtime, constantly pumping in positive charge. Because there must be a positive charge leaking out of our axon. So we have to continually pump it back in.